Hi, everybody. Welcome to the first talk of this season's schedule. And yeah, it's a full crowd. It's great to see. It's a great pleasure to have Jason Bramburger with us, just from down the street from Concordia. Jason did his bachelor's at Nipissing University and then his master's and PhD from Ottawa, which is where he's from. So he was, home grounds. And then he was an itinerant mathematician, going around 5 cities in six years, sort of Paul Erdős style. And then he landed in, so he was at Brown, he was at University of Victoria, he was at University of Washington, Seattle, some postdoctoral positions, some as faculty positions, and then he landed at Concordia as an assistant professor in July 2022. And he has written a book on data-driven estimation of dynamical systems. It's a plug. And but today he will talk to us about, data-driven system analysis using polynomial optimization. All yours.
Okay, thank you very much to everyone for being here, and thank you very much for having me in to speak. So as was mentioned, I have quite a bit of postdoc experience, sort of varying. And so what you're going to see today is really the sort of hodgepodge or mishmash of everything that I've been interested in over a bunch of very different postdocs. So for example, the data part of this is coming from my experience at the University of Washington. The polynomial optimization part is coming from the University of Victoria. The dynamical systems analysis was when I was at Brown. So there's kind of a lot of moving parts in here, and I don't want to get anyone lost or confused more than necessary, maybe. So feel free to stop me. Oh, I think I have my speaker on, pardon me. So feel free to interrupt if you need some clarification or anything like that. But here's your warning, is that it will be sort of bent towards dynamical systems, but everything will be primarily data-based. So really, if you just have time-varying data, you should be okay. Now, as was said, I also think I have an almost contractual obligation to plug this, but I wrote a book about a lot of these things. So what I'm going to talk about today is basically what's coming from chapter 4 of the book. It's going to be published by CIAM by the end of the year. I just submitted my second round of revisions or proofs, so it should be out soon. Now, the nice thing is here, the book goes through a bunch of data-driven methods. Now, they are, again, all bent towards a sort of dynamical systems flavor. And it is example-driven. It's aimed at maybe graduate students, strong undergraduate students, or people, maybe faculty members who really sort of want to get into the area. And so that means that you're not going to find things like proofs or theorems in here. It's going to be example-driven. And the other piece of this is the examples can all be recreated. So you can just go into the GitHub repo. You should be able to just hit run. You should be able to recreate the results, and then maybe put them on your own system if you want to apply them. Okay, so like I said, my background comes from dynamical systems analysis. And when it comes to analyzing dynamical systems, you can kind of take 2 courses of action. Okay, so the main course of action that people take are the ones that you might learn in an undergraduate class on dynamical system. And that's really focusing on specific salient features of a dynamical system. So this is things like maybe fixed points, right? You look at equilibrium solutions to your dynamical system, or maybe you step it up and get a little bit more complicated. You look for things like periodic solutions, you look for connections between them, but really this is a pretty microscopic analysis, right? You're focusing on specific trajectories of the solution and really, really specific regions of phase space, especially, if you start looking at stability of these things, it's always local stability. So of course, when you want to look at dynamical systems from the other side of this, you might want to ask yourself about more macroscopic information about the system. So for example, does your system have some sort of absorbing set or some sort of attractor that everything falls into, right? The specifics of the attractor don't matter, but does one even exist? Or for chaotic systems in particular, it's not very useful to look at specific trajectories of your dynamical system, but it's much more fruitful to look at averaged quantities over these chaotic attractors. Okay, so for example, if you're coming from a fluids background, which most people in the room probably are not, you might ask yourself, what is the average heat transport that's taking place in your fluidic system, instead of, what is the specific heat transport? Or you could ask yourself, what is the pointwise extremal behavior that takes place over a system, right? What are the largest swings that can take place along my system? How far, what is the maximal energy that can be achieved pointwise in my system. And what I'm going to try and convince you of today a little bit is these macroscopic methods or these macroscopic analysis aspects of dynamical systems can be tackled with what are called auxiliary functions. So I'll tell you what they are in a minute, but this falls into what I'm interested in, the auxiliary function methods. Now, there's another way of asking macroscopic information about dynamical systems, and that comes as a statistical perspective. This means putting statistics on the attractor, things like this is where you get into measure theory, probability theory. What's the probability of entering certain regions of phase space, right? And it turns out that this sort of forms the basis of what's called ergodic theory, but it is dual in the sense of optimization to the auxiliary functions method. So anything that I can show you today that's handled by auxiliary functions can also be put in a probabilistic language of tackling through these invariant measures. Okay, so what is it that I mean, right? So most of my research relies on examining what are called auxiliary functions. Now, auxiliary functions sort of pop up in dynamical systems by proving statements about the dynamical system by finding a smooth function that is scalar, so it takes the phase space into the scalars, whose evolution along trajectories obeys certain pointwise inequalities, okay? Now, that's very, very vague, but let's focus on this piece in red for a second, okay? Evolution along trajectories is captured by what is called the Lie derivative. Now here, I'm giving you a sort of abstract representation of this formula, but here my auxiliary function, this is my phi, and essentially what this is this is a directional derivative of your auxiliary function, phi, but it is moving in the direction of the flow of the dynamical system. Now, I'm going to give you everything in the fully stochastic framework, and the reason for this is because everything I'm going to talk about applies to either deterministic or stochastic systems equally, okay? Now, if you don't like the expectation here, just get rid of it, do pointwise evaluations, right? But this is, you can talk about these things as expected directional derivatives as well, okay? Now, okay, maybe you don't like this, maybe you find this a little confusing, maybe you work with ordinary differential equations most of the time, right? Well, the Lie derivative is easily explicitly computed. It's just a chain rule evaluation, but essentially it's the right-hand side dotted with the gradient of your auxiliary function, okay? Well, maybe you spend your time working on maps instead, right? Discrete time dynamical systems. Again, the Lie derivative is sort of easily computed here. It's a sort of composition with the right-hand side, and then it's essentially just a discrete derivative, right? Or maybe you spend your time doing stochastic differential equations, right? Well, again, you can explicitly compute these Lie derivatives. So really all I'm trying to convince you of is like any sort of Markovian process has an associated Lie derivative. If you come from that area, you would refer to these things as the generator. And this framework that I'm going to describe to you applies to basically any type of dynamical system you can come up with. It's going to be very, very difficult for you to come up with one that doesn't fit this, at least as long as it's a Markovian process. Okay, so what's an example? So if you have taken a class on dynamical systems, this is the one that most people might see. And the example of an auxiliary function here is a Lyapunov function. So in this case, you can see that I have an auxiliary function because it takes in my phase space, it spits out a real number. It satisfies a bunch of pointwise inequalities on the thing. So here you have this sort of opening upwards, but the real important aspect here is that the Lie derivative is negative. Notice that I just wrote this abstractly. Most of the time you see this for ODEs, but this applies to stochastic systems or anything else as well. You can find Lyapunov functions there. And essentially this second condition, this is your sort of flowing downhill condition if you are familiar with Lyapunov functions. This is a sort of prototypical example. It shows global stability of, it's used to show global stability of solutions of these systems. And you can extend this in a whole bunch of different ways. So you can apply things like the LaSalle invariant principle. You can use sort of variants of the Lyapunov function to find forward reachable sets in your dynamical system. So what is possible if you move forward in time? Some work that I played around with was constructing barriers and trapping regions. So finding these chaotic attractors, for example, locating them in phase space, seeing if you actually have one. They can all sort of be put into a similar framework. The important thing is Lie derivative pops up and inequalities pop up. That's all that you should take away from this for now, okay?
So
Yes.
V, the Lyapunov function, does it have to be differentiable? Any conditions when you apply the Lie derivative?
You should, yeah, so usually if it's ODEs, this is gonna involve a gradient, so you're gonna have to have a differentiable function, so it would be, yeah, you have to have a C1 function.
C1
here, yeah,
function,
yeah.
okay.
But if it's discrete time, it doesn't matter, it can be piecewise continuous as well.
So for instance, the phase of the oscillator, would that work? The phase of an oscillator,
For what?
or as a, let's say you take the direction of the phase, is it well defined?
I'm not sure, I haven't
Okay.
thought about it. I mean, the phase isn't gonna give you global stability, right? Unless is your oscillator globally stable that you're thinking of?
Yeah, I'm really thinking about the phase of an oscillator, like define d phi over dt equals 1, so I guess the lead direction is just 1. But I'm wondering if you're not on the limit cycle, I don't know exactly what.
Yeah, if the limit cycle is unstable, then absolutely not, right? Yeah, yeah. So, okay, Lyapunov functions are the sort of prototypical example, but they're not the example that I care about as much. What I really care about are sort of answering those more macroscopic questions. And as I said, there are ways, or there are things that you could be interested in, particularly where I'm coming from chaotic systems, of looking at time averaged quantities, right? So what's the average energy that the system displays? Or if you're talking about a fluidic system, what's the average heat transport? Or what is the average dissipation that's taking place in your system? So this is quantified by, say, taking some quantity of interest. So this would be energy, heat transport, whatever it is that you might be interested in your system. I'll just call it a quantity of interest. And what you're going to do is you're going to take infinite time averages over trajectories of this thing, okay? Now, it turns out that you can tackle these things using auxiliary functions. And essentially what you can do is you can identify an auxiliary function v and an upper bound u. If they can satisfy this pointwise inequality, then you can show that your infinite time average is bounded by this value u. Now, the beautiful thing here is you never have to simulate the system to do this, right? You just need to put in points from the phase space. You never have to actually take a time average. Now, you can, the other nice thing about this is this applies to a class of initial conditions, not just a single initial condition. If the space where you're picking all of these x's from is forward invariant, if you're stuck in it, if it's a chaotic attractor, for example, right? This will give you the time average over all possible trajectories on the attractor. What is the maximal dissipation that can be achieved by this thing? In fact, you can go further. You can say that if this thing is compact, again, think chaotic attractor, for example, you can prove that there is an auxiliary function that exactly hits the maximal upper bound. So if your maximal energy over your entire attractor is 2, there is an auxiliary function that will give you that exact upper bound of 2. And so that comes down from up top. Hidden inside the optimal auxiliary function is information about the specific trajectory that is going to maximize that for you. So again, think about if you're a practitioner, if you want to maximize heat transport in a fluid flow, for example, first of all, I can use auxiliary functions to tell you what the maximal value of the heat transport would be. Then I can dig into the auxiliary function and tell you exactly which trajectory is going to maximize that heat transport so that I could potentially control it. I can entrain the dynamics to maximize that transport.
Jason, can I ask a question?
Yeah, please.
So this depends on the auxiliary function v.
Yep.
And you say optimal auxiliary function.
Yep.
What does that mean?
You have to, so any v you pick, you find the best lower upper bound, right? That's associated to it. Now you can imagine playing this game of trying to bring down the lower bound by picking v's. So when I talk about the optimal one, it's the one that gives the exact upper bound in terms of this equation that hits this exact top of the time average. But you can always approximate this, right? You can find sequences that converge in. I mean, I said right like you knew, but that's you can always approximate these things. Now, the other aspect of this is you can do something similar. I'm not going to go into this too much, but you can do the same thing using auxiliary functions to get pointwise swings over attractors, right? So for example, if your dynamical system is sort of spending a whole bunch of time over here, and every once in a while you have this huge outgoing trajectory and this huge swing in the dynamics that you maybe even don't see whenever you simulate this thing on really, really long timescales. So for example, pole switching of the of planets, right? You can actually find out what those maximal swings are based using these auxiliary functions. I won't go into this one too much because it's just a little bit more involved, but again, there it is. Lie derivative auxiliary functions. Yes, please.
Super dumb question.
Please.
Is it, how easy or difficult is it to find these functions? You're
Next
talking-
slide.
Okay.
Yeah. It's very hard to find these, okay? If you have ever tried to find an auxiliary a Lyapunov function, you will know that this is the worst advice anyone can give you in dynamical systems, right? Have you tried looking for a Lyapunov function? Where, right? Where would I ever look? Because what you will notice about this is the auxiliary part of auxiliary functions is they have nothing to do with the dynamical system. You have to find them and put them into the equations in order to say something about them. But I have an algorithm that can help you with this. So for example, if I assume that the dynamics of my model, I'm going to assume I have an explicit model for a second. If the model is polynomial, okay, and you can abstract this to a whole bunch of different systems, but let's stick with polynomial. Right? What you could do is you could look for polynomial auxiliary functions, right? So this might be as simple as just expanding, as a sort of Taylor expansion, a monomial-based expansion. And the first thing that you can show here is that the Lie derivative is polynomial too. Now, if you're mentally keeping track of everything in your head, that means that now you've reduced yourself to verifying a bunch of inequalities based on polynomials, right? And essentially, you're going to play this game of tuning coefficients to satisfy these inequalities. That's great, right? Unfortunately, it's not. This is a terrible thing to do. It turns out that you can prove that this is NP hard to try and tune coefficients of polynomials to make them non-negative over sets. This is next to impossible when the degree is high or when the number of variables is high. So we're back to square one. But it turns out there's a computational relaxation to handling this. And you can replace inequalities with what are called sum of squares constraints. Now, sum of square polynomial is exactly what it sounds like. It's a bunch of squares added up. What we know about squares, they're non-negative. If you add a bunch of them together, they're again non-negative, right? So x squared plus y to the 4 plus x to the 6 times y squared, right? These are all simple things that you could just look at and say this is non-negative. It turns out that this is a strengthening condition. It's not equivalent to being non-negative, but you can replace all of these inequalities, with these sum of squares conditions. And what's fantastic about this is sum of squares constraints can be translated into semi-definite programs. Semi-definite programs can be solved on the computer. And what that means is you can identify the coefficients in the spin using semi-definite programming solvers.
Are you saying that they're Lipschitzian, like they satisfy Lipschitz condition?
What satisfies the Lipschitz?
Like this sum of squares. This sounds to me more like, follows this criterion, Lipschitz condition.
X squared isn't a Lipschitz function, right? But
Yeah.
It's a sum of squares.
Okay.
No? I'm not sure. I'm not. They don't have to be Lipschitz, right? And in my case, I'm just talking about polynomials. But x squared is a globally non-negative function. It's also a sum of squares.
Okay.
So let me show you a really simple example with Lyapunov functions, okay? Here's my simple ODE. I sketched down a vector field. I threw it into like Wolfram, and I sketched down a vector field. And what I look at here is it looks like everything's sort of spiraling into zero, right? It looks like zero is a globally stable state. I've got a polynomial dynamical system. So what I could do is I could look for a Lyapunov function here, right? A Lyapunov function will tell me that zero is globally stable. And so what I can do is I can computationally look for a Lyapunov function v that satisfies these conditions here. Now, is SOS means it can be reformulated as a sum of squares. If it can be reformulated as a sum of squares, it's immediately non-negative. So that verifies that this thing is greater than or equal to zero. Now, why do I have this piece right here? This is a coercivity condition, right? This means that it really does open up. The only place this thing is equal to zero is at zero. There's all kinds of different ways to do this, But now look at this condition. This is sum of squares as well, greater than or equal to 0. I rearrange, it says the Lie derivative is negative. That's again, the second condition that I needed for my Lyapunov function. And what you can do is you can expand out these auxiliary functions. In my case, I expanded as a degree 4 polynomial on both of the state variables. And what you can do, you can solve this quickly and efficiently on a computer using these interior point methods. And you pop out all of these coefficients that tells you that this thing is globally stable because I've at least numerically identified a degree 4 auxiliary function, a Lyapunov function. So these are all just numerical coefficients. I could spend the entire talk talking about sum of squares methods. I don't think you want me to. And so what I want you to understand here is that I can find auxiliary functions using these methods, okay? That's really what I want you to take away from this. This is a whole field of algebraic geometry if you really want to get into it. And there's all kinds of fun that can be had and all kinds of hard problems. But again, it can be done. That's what I want you to understand. So here's what we've said so far, right? You can use these sum of squares methods and semi-definite programming in order to find auxiliary functions. But again, this is under the assumptions that my right-hand side is polynomial, right? Now you can extend it. There's all kinds of things that you can do. You can extend it to, say, trigonometric or all kinds of fun right-hand sides if you wanted to. And in particular, you can establish convergence results. So you can say that maybe as the degree of the polynomial basis that you're expanding in goes up, you are converging to, say, like the best Lyapunov function, or as James pointed out, the sort of optimal time average bounding function. As I said, there's a dual side of this where you can approximate densities of invariant measures as well using their moments, their polynomial moments. But here's the thing, this is all pretty well established stuff. Okay, this is stuff that I have worked on before, many other people have worked on before. But what we would like to be able to do is we'd like to do this in the absence of having the dynamical system itself, right? So for example, if I give you a bunch of data from a system, can you tell me that it's globally stable? Can you find a Lyapunov function to prove that it's globally stable? Or if I give you a bunch of data from a system, right? Again, think about that, my pointwise swing example. You're spending all kinds of time seeing something happening over here, but after millions of years or something, there is a massive pointwise swing that's not going to be observed in the data, right? Can you use these auxiliary function methods to show that that pointwise swing is actually going to take place if you're just observing data in one region of space? And that's where I want to focus the second half of this, okay? So this is where the sort of famous, or at least currently famous, at least in dynamical systems, Koopman operator comes into play. And so this was originally formulated by B.O. Koopman in the 30s. In fact, what Koopman was trying to do was he sort of had a little bit of envy, a little bit of jealousy over what was going on in quantum mechanics at the time. So the quantum mechanical formulation of putting everything in terms of functions and working on Banach spaces. What Koopman was trying to do was trying to do the same thing for dynamical systems analysis. And what he came up with is what's called the Koopman operator that is named after him. So in this case, what the Koopman operator does is it pushes dynamics forward in time through what are referred to as observables. Now, this is going to sound familiar for a second, but an observable, this is a scalar valued function on the state space of your dynamical system. And here is the Koopman operator. It says, where am I now? If I know where I am now, then where will I expect to be inside of the observable? So if I know the energy of my system now, what do I expect the energy to be in some future time, right? If I know the dissipation right now, what do I expect the dissipation to be later, right? So observables are pretty aptly named because this is how most practitioners are going to give you data, right? They're not going to give you the exact observed state dynamics of the system, but they'll give you maybe glucose levels of the body instead of giving you, the million different variables that go into producing those glucose levels. Now, again, I'm giving it to you an expectation. You don't like expectation, that's perfectly fine. That will do, right? Just get rid of the expectation. But here's the important part. The Koopman operator is intimately related with that Lie derivative that I'm obsessed with. The Lie derivative turns out to be the infinitesimal generator of the Koopman operator. So informally, you can think of the Koopman operator as being e to the power of the Lie derivative, kind of if you think about linear dynamical systems, e to the at or something like that, right? So essentially, you can see for discrete time or for continuous time, you can see these formulas. And the reason I find this so exciting is because the Koopman operator is very, very well studied in the past 10 or 15 years. We're currently living through what's referred to as Koopmania. And there are a lot of people, everybody and their dog in dynamical systems is writing a paper about the Koopman operator. And that means that there is a lot of useful information that we can leverage from the Koopman operator side of this to bring back over to the auxiliary function side of this. And in particular, there is a whole bunch of work being done on approximating the Koopman operator on data. And if you can follow my logic here for a second, if I give you data from the system, I can approximate the Koopman operator. If I can approximate the Koopman operator, I can approximate the Lie derivative. If I can approximate the Lie derivative, I can answer questions using auxiliary functions. Now, the most interesting point that in that chain there is that at no point did I ever have to do model discovery. I never had to try and figure out what the underlying model is to this thing. I took the data and I gave you information about the system. I never had to know what the system itself is. So let me show you the process, okay? The way that we're going to apply this is using what's called extended dynamic mode decomposition. So the name isn't really that useful if you're not sort of familiar with dynamical systems, but here's the basic setting. I give you collections of data. Okay, what's happening now? What's happening at one time step in the future? Okay, so you can pair out the data like that. It doesn't have to come from the same trajectory. They can be sampled from all over the system as long as you give me pairs. And what I'm going to do is I'm going to introduce two different dictionaries or libraries of auxiliary function, or sorry, of bases, function bases that I might be interested in. One I'm going to call the expansion dictionary, one I'm going to call the image dictionary. I'll show you why in a second, it'll make sense. But here's the basic idea. I can approximate the Koopman operator acting on my expansion dictionary with one line of linear algebra. I mean, one MATLAB code line, right? Essentially, I'm evaluating all of the data points inside of each one of these libraries, building these huge matrices. And it's a pseudo inversion, right? Because these things are probably not going to be invertible. So I need to get the best approximation of an inverse. Multiplication. I mean, this is literally like the whole thing. This whole slide is probably 3 lines of code if you really wanted to do it. But here's what it does. That approximates the Koopman operator on the expansion dictionary. So what could I do? I could look for auxiliary functions in the expansion dictionary. I could expand them in that dictionary. So for example, if I want to do polynomial optimization, my expansion dictionary should be a bunch of polynomials, right? Up to some fixed degree, okay? Then what I get from this is an approximation of the Lie derivative, in my case, just using a finite difference approximation here of the Lie derivative. That's my matrix Koopman operator acting on my auxiliary function minus the auxiliary function itself. Now I've got access to an approximate Lie derivative. If I have access to an approximate Lie derivative, if both of these things are polynomial, I can do polynomial optimization, and I can take all of the stuff that I showed you from the beginning of this talk for finding auxiliary functions and just replace the proper Lie derivative with this one approximated from data. Let me show you how it works, okay? Oh, sorry. Let's take a really simple example. Okay, so this one is, again, it's coming from mechanics. I'm going to look at what's called the van der Pol oscillator. Okay, so it's it's a system of ordinary differential equations in this case. Now, the system is very, very well studied. It's very, very simple. But essentially what we know is that eventually this thing is going to fall into a periodic oscillation. So I'm showing you the phase plane dynamics up here. And what I would like to know is what is the maximal energy, the maximal time averaged energy of my system that can take place. Okay, so because it falls into a steady oscillation, the maximal energy is going to be on that steady oscillation. It's going to be the time averaged energy around that thing. So one thing that you could do is you could just wait right? You could just average the data as it comes in. And this is exactly what I'm doing in the bottom left corner, right? So as time runs, I just take the data and I take the average, and I can see here it's running up, right? It's sort of, you can see it almost starting to plateau. But take a look at this. Because I started very far away from the oscillation, I started really close to the center here. It takes a long time to average out, right? So the actual average I'll show you in a second is about 4.0 something. So we're still pretty far away, and we've been running this for 250 time units, right? Alternatively, what I could do is I could feed in that data that's seeded at maybe this part, and I could get an upper bound using my bounding mechanisms that I showed you previously in order to come up with bounds on the maximal energy output of the system. So here is a big, horrible table for you all to not spend too much time looking at if you don't want to become seasick. But here's what I want to show you, okay? Degree of V, this is the degree of your expansion dictionary, okay? Up to degree 4, 6, 8, 10. This is the time that you give me data up to, from time 0 up to time t. This is what would happen if you took the empirical average. You just took that data that I gave you and did this. You took the average of the data that I gave you, give me the energy. 2.24, we're very, very far from the actual value. But take a look at this. With hardly any data, I can look at degree 10, I'm at 4.01 is what I've put an upper bound using auxiliary functions on this thing. Now, I can actually use the exact Lie derivative to figure out what the exact upper bound is with a bunch of, sort of proofs hiding in the background. The exact maximal energy that could be output in this system in the time average is 4.0012. So with integrations up to only 100 time units, so we're going to cross it again very, very quickly. Look at how far away we are from this thing being where it should be. We can get a lot of information on this system. And that information is the information we're using to leverage this is very, very far away from the steady oscillation this is supposed to fall into. Okay. So why does it work? Well, it turns out that we have, the paper that this comes from is full of proofs, and we can actually say exactly why this works so well. So here's the thing. There's a bunch of people that have worked on this, myself and my collaborator Giovanni. We extended all of these results to fully stochastic or Markovian process systems, okay? And I'll show you exactly where this comes from in a second. But essentially, here's the basic idea. You either sample, you take your data, and it has to be sampled from some distribution. I can go into this in a second, but here's how you can satisfy it. You take either data from one long trajectory that sort of feels down phase space, we call this an ergodic trajectory, or you can just independently sample the system for maybe short little bursts or just one point in time, okay? So that as long as you use one of these two strategies to sample your data, then what you can prove is that your Lie derivatives, they converge. So here is a whole bunch of things. This is in the amount of data. This is in the size of the expansion dictionary. This is in the size of this is your sampling rate, okay? The reason it says almost surely is because this is coming from the fact that you're randomly sampling data. If you keep randomly sampling at a fixed point, you're not going to learn anything about the system. So, this holds in probability. But what does this really say? Well, there's something very interesting hidden in the proofs here. As we've gone through this whole talk, I keep giving you everything in the fully stochastic formulation, right? I keep talking about expectations, and maybe you don't like it, but the reason I did it is because our convergence proofs, not the ones that were done previously, they show that that you will converge to the right Lie derivative no matter what. I don't care about how the data where it comes from. I don't care what the system looks like. As long as you give me the data, and as long as it's sampled according to this, I will get the right Lie derivative. At no point do you have to tell me that it's deterministic or stochastic data. I will converge to the right Lie derivative no matter what. The only thing that this method is seeded by is the data that comes in and my choice of libraries. Okay. So there's also another sort of weird thing that's sort of hidden in here. This goes back to why we worked so well on the previous page. But if you'll notice, this is L2 convergence. You might not like L2 convergence. It doesn't really converge the way we want things to a lot of the time. But actually what's hidden in the proofs is we can prove pointwise convergence to the lead derivatives. And pointwise matters for us because we are evaluating those sum of squares conditions pointwise as well. Okay, let me show you some things that are much more recent here. So this is some work with my departmental colleague, Simone Brucciapaya, and our joint master student, Daniel Fassler. And so Daniel's really been heading up this great project where he's been looking at how should we gather the data to make these results as good as possible to get it. Because if you look at this converges to 0. Great. Right? How does it converge to 0? What's the best way to approximate the lead derivative if I give you a certain number of, or if you only know that you can sample the system at certain points or for a certain amount of data? And so the first thing that Daniel was able to show is something that's probably familiar to you if you're familiar with Monte Carlo integration. But you can show that if you just take IID samples, so and you have an orthonormal dictionary, you get convergence of the lead derivative to the, what is it here? To the projected lead derivative onto your finite dimensional image dictionary at this 1 over square root of n convergence, right? So this is, if you are familiar with Monte Carlo, you might recognize this, but in some sense, it's not very fast, right? But Daniel has done a whole lot of work here, and he showed that it doesn't really matter what measure you're sampling from, or sort of what probability on your space. It doesn't really matter what functions you're using here. These are all just constant prefactors. Everything is converging at this Monte Carlo rate. Now, of course, this is not particularly fast, right? This might require you to have a whole lot of data to get good approximations. And so what Daniel's actually been looking at is doing this better. Is there a way that we can speed up convergence? If I know that I only have a certain number of samples, right? Maybe it's really expensive data to gather, right? I can only gather maybe 100 data points, or whatever it happens to be. How can I do the best I possibly can? How can I optimally sample this thing in a timely, sort of timely and efficient manner in order to get the best approximations of my lead derivative? Because again, I need a good approximation of the lead derivative to apply the auxiliary function framework, right? If the lead derivative is junk, the results are going to be junk too, of course. So what Daniel's actually been showing here, or what he's been looking at, is you can speed this up to exponential convergence. Now, exponential is a whole lot faster than 1 over the square root of n. And the way that you do this is you have to very strategically grow the size of your expansion dictionary. Sorry, your image dictionary, pardon me, that's what this M is. You grow the size of this image dictionary with the number of data points you have. This is what he's showing right here. So for a whole bunch of different sizes of the expansion dictionary, M, you can rearrange these things, but here he's writing the number of samples in terms of the size of the expansion dictionary. If you hit these things just right, if you grow the dictionary with the data that comes in, you can get this beautiful exponential convergence. It's rapid, right? It's really, really good results for relatively cheap amounts of data, right? You could do this for 100 data points or something like that and get very, very accurate lead derivatives. And again, very accurate lead derivatives means accurate information about the dynamic.
This is like a trial and error kind of thing, like
No, these are proven. These are all well known. Yeah. This comes from Simone's work. Simone, my collaborator, does a whole lot of function approximation. And it turns out that a lot of what Simone is working on in function approximation, sort of applied harmonic analysis, if you put it in the right context, turns out to be the same things that we care about in dynamical systems. And so what Daniel's been doing very, very well is sort of helping to translate, transpose a lot of these results, as well as extend them to being applicable to these approximations, the Koopman operator and the lead derivative. You got a question too? Yeah.
Yeah, you just back to the next slide.
Yeah, for sure.
So, okay, so is this a theoretical result that you derived?
This part is theoretical. This is just an application, right? But yes.
Yeah, okay, but I want to ask about this application because if you increase the dictionary, like as a function of m squared log m, that's gonna result in a Koopman operator that numerically might be really poorly conditioned.
Yes, yeah, so.
And so there's
Yeah.
like, I guess what I'm trying to point out here is there's another trade-off, right? Which is the numerical stability of, and I'm gonna use something you might disagree with, of the model you've identified from data.
Yes, I agree. However, there's one piece of this that might be discounted, and that comes to the fact that the Koopman operator that I'm learning is rectangular. It's not a square Koopman operator, right? So it is the size of the expansion dictionary by the size of the image dictionary. So you have a little bit of leeway here because you're not growing in 2 dimensions at once, right? But yes, of course, you're correct, right? However, the nice thing about an exponential convergence rate is these things can be relatively small, right? We could be talking about 50 data points or something like that and get really small errors without making a huge Koopman operator. But I agree. I mean, if your system is 100 dimensional, then I mean, taking m bigger, like I mean, taking anything more than quadratic, you're screwed. Yeah, yeah. This is where our neural network is going to have to come in or something like that. Yeah, but I agree. Yeah. Okay, so I have a long application that I don't want to show because I don't think it's that interesting. I would like to just finish by talking about something that I think, you know, even though it's coming from the fluid dynamics problems, I think that the ideas could be useful to a larger audience. Okay, so what we decided to look at here is a shear flow model. So this is ongoing work I've been doing with David Galusk, and he sort of brought this attention, or to my attention, because he's really a sort of fluid dynamicist. But the basic idea here is you have some sort of fluid bounded within a medium, and you're sort of moving the top and the bottom in the opposite way, sort of shearing the flow here, right? Now, essentially, this is going to be modeled by a Navier-Stokes equation. You have this sort of sinusoidal forcing. This is describing the shearing. That doesn't matter too much. Here's what's interesting, is that no matter what the fluid viscosity, so this is all captured through what's called the Reynolds number. It's the main parameter for fluid systems. The higher the Reynolds number, typically the more complicated, the more turbulent the system is going to be. What you can show is that this sort of sheared laminar flow, so non-chaotic, just this sort of moving with the shears, this thing is always a stable solution to your Navier-Stokes equation. So that means that as long as you start close to the sheared laminar flow, you will stay at it. You will not develop turbulence, okay? However, if you start by shaking up the liquid or the fluid, then start shearing, what you will find is that the larger that Reynolds number is, you will get longer and longer lasting turbulence in this model. So it'll be very, very, very complicated. But if you wait for a long time, eventually it will settle back into the laminar flow. Now, what people would like to know in this is this more complicated turbulence that develops in the model. This is coming from a chaotic attractor in the system. And people want to know when this chaotic attractor comes into existence. At what Reynolds number do we lose global stability of the laminar flow and start developing these turbulent transients? Okay. Now, we haven't got, I know that I've described this in terms of a shear flow model. We haven't got it all the way up to the fluid models yet, but what we've done is we've used a really sort of simple projection of this due to Moelis and some collaborators, where they project this fluid flow onto 9 faithful modes. So these are sort of Fourier modes that capture very well the dynamics of the system. And so Moelis and collaborators wrote a whole bunch of papers about how well this thing captures. So we're going to use this as a proxy for the moment. And so what we're going to do is we are going to generate time series from this Moelis system over a bunch of different Reynolds numbers. And this is going to be captured in sort of our data here at a bunch of different points in R9. Then what I'm going to do is I'm going to take that data, I'm going to project it onto 3 random features. Okay, so all I'm going to do is generate 3 random orthogonal vectors, and I'm going to use my data to seed my auxiliary function methods as just being the projection at each point in time of my 9-mode system onto these random orthogonal components, okay? So that means that I went from an infinite dimensional shear flow model down to a 9-dimensional ordinary differential equation down to 3-dimensional data, okay? So I just kept collapsing things. Then, what I would like to ask myself is what is the maximal time average that, say, the energy of my 3 components can take on? Again, it doesn't really matter what you use as your quantity of interest here, but here's what I want you to understand. If the only thing in the model, if the only state in the model is the laminar state, then the energy is going to be 0. In the time average, everything goes into the laminar state, and so the maximal bound on your quantity of interest is going to be 0. If there exists even one more state in there, it's going to have some energy. And so that means that the upper bound on this thing is going to be positive. It will be non-zero, right? So if there's any other state, it's going to have some energy in it. So what we do is we see if this works. So we throw this into the bounding mechanism that I showed you a few slides ago. If you don't remember it, that's perfectly fine. But essentially what I'm showing you here, I don't know why this is fuzzy, but what I'm showing you for each of the curves is a larger and larger size of your expansion dictionary for your auxiliary function, okay? So for example, for the blue curve, this is an auxiliary function expanded up to monomials in the 3 variables, x1, x2, x3. These are the projections on the random components in degree 5 in those 3 variables. So here, you can see up to Reynolds number about maybe 18 or 19, it's sitting on 0. It says there is nothing there but the laminar state from the data you've given me. But eventually it kind of comes off 0 and it says, okay, well, these are upper bounds, right? An upper bound on my age is 100,000, right? It's not a great upper bound on my age, but it's still an upper bound. So there's still, there could be something else in here, but I'll give you an upper bound. Okay, then we increase the degree of v. That means that I'm increasing the space of functions that I'm searching over, right? No longer degree 5 functions, all the way up to degree 7 functions. Well, then it tells me, okay, there's nothing up to about Reynolds number 29 in this system. But again, okay, well, upper bound on Jason's age is 100 now, right? Okay, then we keep increasing, keep increasing, keep increasing. Again, this is seeded with data, so the lines are not going to be smooth, right? You can prove that these upper bounds, they don't have to be continuous. So you get some junk, but take a look at this. When we get to degree 11, degree 13, these two things are showing a sharp transition from nothing to something at almost exactly the same point. Now, what's interesting about this is that point is about 80. What Moelis shows in his original work with the exact system is that the transition to turbulence takes place at 80.5. That's about as good as you're going to get with this data-driven method, right? So what we are particularly excited about this, and what we think the promise here holds, is this can be used for detecting when you have transitions, phase transitions in data, right? Because the phase transition comes from always having the laminar state and then having something else with positive energy that bifurcates into existence that you do not see. You feel the effects of it eventually, but you do not know when it sets in. And that's what we're able to sort of find here.
Can
Yeah,
I
please.
ask a question here?
Yes.
I'm gonna admit that I don't have all the details here, but I'm
Okay.
just gonna ask the question nonetheless, and it could be quite naive. So here you're making a prediction about the phase transition, which is great.
Yeah.
Is there a possibility that you're overfitting? I mean, would the Bayesian approach in terms of having too many parameters? I mean, you're decreasing the degree of the polynomial here, so you're increasing the degrees of freedom. So maybe, I mean, it worked here, but doesn't mean that it worked every single time.
Yeah.
So how would you have a guarantee that you're not overfitting as opposed to doing the right thing?
Yeah, I agree. I ran this 2 weeks ago, so this is all that I have empirical observations at the moment. Point taken, right? I completely agree. I mean, the one of the main hyperparameters is how many random modes you project onto, right? If you use less than 3, you get junk all the way, and junk in, junk out.
Mhm.
If you use more than 3, then libraries start to become, monomials in 4 variables start to become pretty complicated, especially as you get up to degree 13 here. So, okay, then you got to trade off how much is my time worth versus what kind of accuracy I want. The only thing that I can say is that we have a success. We have one success. I don't know how many other failures, but this is promising for us because this is just distilling what could be potentially very high dimensional data using a random feature method and using those random features to find things about the original model, which we have, again, no knowledge of, right? We don't even know what the exact leader looks like here. You could maybe figure it out if you work backwards, but point taken, point taken. Yeah. Yes, please.
Is the random feature very important? The random part, this is again back to compressed sensing or something like that.
Yeah, so there's all kinds of these results. If Simone is listening about, you can get these almost surely results in terms of the random features. I've tried it with a couple different random features, like just generating random orthogonal vectors. I don't see a whole lot, right? And but again, this is the Wild West. If anybody has a suggestion, if they have a proof, or if they have a counterexample, keep your counterexamples to yourself. But for the most part, if you have ideas, I'm all for it. I mean, I'm not kidding. I literally did this 2 weeks ago, and I was like, oh, I want to talk about this because I think it's cool. But yeah,
Is there also scope for detecting time non-stationarity when something is about to happen, something bad, for example? So this was in the base space for the Reynolds number, right?
yeah.
But you could also be watching it to say, oops, the stock market is going to go crazy or something.
Yeah, there's David Gluskin, who's the guy that I've been collaborating with this. He was my advisor at the University of Washington. He did some of this stuff, these finite time extreme events, using auxiliary functions again. So it fits within the framework. I've never done it myself. With the stock market, good luck. Yeah, but yes, but the answer to that question is very much yes. It can be done with auxiliary functions. I'm not familiar with the specifics of it. Yeah.
A question.
Yeah, please.
Can at least using low polynomials, once we get the information that there's like a spike or something in the system, so we can know that there will be a turbulence, but we don't know exactly when it will came. And can we at least say that this information is true? Once we get this like spike in the low polynomials at least.
Yeah, so you mean actually, I mean, I guess you're looking at this, but you're talking about this spike right here. Yeah, so this is a wonderful thing that we do in dynamical systems where we ask questions where we already know the answer, right? And so I already knew what to look for here. So of course, I could say whether or not it worked. You always have the problem when it comes to data is that are you giving false positives or just straight up negatives? The one redeeming aspect of this is all of those proofs that I have for the approximation of the leader derivative, and at least tell you asymptotically the results should be correct, right? So the more data you generate, the better your approximation should be, and the more realistic they should be. That's all that I can really say for now. Mm-hmm. Okay, let me wrap it up. Okay, so what I really want you to think about here is the unification of a couple different ideas: dynamical systems analysis, and primarily through auxiliary functions. That's where my heart will always be. That's the stuff that I love. But this is done through the incorporation of methods from algebraic geometry. These are positive polynomials using sum of squares techniques, and this is done in a completely data centric way using the Koopman operator. Okay, now again, think about how this works. At no point do I actually have to discover the underlying dynamical system. And this is a good thing because, as I told you, this applies equally to deterministic and stochastic data. Discovering stochastic systems is a whole can of worms you do not want to have to find yourself getting into, right? So I can skip it completely. I can get information about the dynamical system without having to do model discovery. Now, the last part of this, I had mentioned that there is a dual formulation to this, dual in the sense of optimization, if you're familiar with it, that can be used to get invariant measures of your dynamical system as well. And this is something Giovanni and I have written a paper about too. Essentially, it uses the dual operator to the Koopman operator. This is the Perron-Frobenius operator. So with all of that being said, I would like to thank you very much for your attention. And if you want to learn more about this, this is really coming from two papers primarily that spell out most of this theory. So thank you.
Yeah, thanks, Jason. That was great. Other questions?
We'll start there maybe.
Yes.
Sure, yeah.
So that was great. I was wondering, okay, so it's a very naive question, but so you have a very dynamical system standpoint.
Yeah.
And, I could also take, so I'm a physicist, so I could take a physics standpoint and say, let's say I have something like Ising model and a Hamiltonian, and I do metropolis dynamics on it. And then I could try to fish for a phase transition for something like this. Like, is it super easy compared to what you do, or is it the same kind of difficulty, or is it an interesting problem?
It depends on what you would classify as the difficult part of
Yeah.
it, right?
I
So
don't know.
if your difficult
You tell
part
me.
is simulating the system,
Yeah.
for example,
Yeah,
then this could potentially be easier, right? So
Okay.
if you have a really complicated model, like for example, with the shear flow. Shear
yeah.
flow is a pain to simulate, right? So
Okay.
that's why, for example, the stuff that I talked about that Daniel is working on, trying to use the least amount of data to get the best results, right? Because eventually I do want to set this up to more complicated fluidic models, for example. I don't want to spend my time generating data from fluid models. I mean, my life is short, right? I don't have that kind of time. So, however, the alternative side of this is if you have the system, for example, I always said Ising, but Ising?
Ising,
Yeah,
I
you're-
say Ising, but I'm.
You're probably right. I
I don't
mispronounced
know,
everything.
my accent is not that good.
But-
I think it's Swedish or something like that, so I have no idea.
But if you have the system, work with it. Use the information you have, right? So why use a data method whenever you have the system? Unless you're doing what I'm doing, where you're trying to get some
No, but-
experimental validation.
I was thinking about this because you have say biological data, and you will model it with something that can be related to the Ising model. So that's why, connecting it to something like an Ising model in the first place would be interesting, because then I could look back at my biological data and figure out what happens.
Yeah, so that's another thing that I've actually worked on that I didn't talk about here, but using autoencoder neural networks to transform data to fit these sort of canonical forms. So I talk about this a lot in the book as well. It's chapter 6 of the book, where I talk about transforming between canonical systems and getting in, which is great, so I can analyze, but also getting back out, right? So yeah, thank you.
Okay, first of all, I really enjoyed your talk, and
Thank you.
it's been a while since I've attended a math talk, which is great. So I have two questions. The first one is related to stochasticity. I mean, I work with the neural data, and the neural data notorious for being quite stochastic. So, it does happen that some neurons which generate these large excursions, the action potentials, very rarely. You have these rare events that take place, and they occur because of a stimulus, not because it's embedded within the data. So how can you predict these kind of rare events that are not embedded in the data, but due to actually a stimulus, an environmental factor that is coming in? Because you emphasize that it works with stochastic models, but stochasticity might not be within the data, but actually due to environmental factors.
Include the
Are you nodding because you have an answer?
But that's a control input.
Yeah, that's what I was
That's
gonna
what
say.
I'm
It sounds like,
saying.
yeah,
And you have a whole way of modeling this with control inputs.
yeah.
There's a whole extension to all this theory to account for an external stimulus on the propagation of the dynamics.
I was gonna try and hand this over to James as
Okay.
well. Yeah,
So-
you can extend a lot of this to control systems, and I've never seen anybody try to do much beyond the Lyapunov function stuff for control systems, but this might be actually worth looking at. By the way, James and Stephen and I have an extension, I didn't talk about this, but to control systems as
Okay.
well, but it's for stabilizing primarily. But yeah, one of the things that has made Koopman, the whole Koopman universe theory of dynamical systems so important is its application to control systems. Gives you a nice linear description of dynamics, then a lot of these well-developed ideas from control theory follow quite nicely.
Yeah, can I just follow up on that for a little bit? So the standard Koopman framework is really for unforced systems. Given an initial condition, we want to fit some data to predict, the evolution of some sort of dynamics. But the extension we're talking about is there's been people who've worked on, okay, how do we predict outcomes when we know the input that's been applied to the system, all right? So like systems with forcing, basically. So you can do a lot, in fact, like we wrote this paper, the three of us, where we explicitly look at, well, how do you actually design even controllers to get the response you want when you have control over the input, for example. Okay, so there's like a whole extension to all this to handle force dynamical systems that use a lot of, like a lot of the same tools that Jason's been talking about.
Okay.
The
Question?
short answer is it's possible. It requires a little.
I mean, yeah, obviously, it's nice to know that it's possible.
Yeah,
I don't,
yeah.
I mean, I
You
need to
can
learn
live
about the
optimistic,
details.
right? Yeah.
There's a question from Victoria in the chat. I can ask it for Victoria. Victoria asks whether the library has to be polynomial. Can it use rational functions or exponentials, etc.?
Yeah, great question. I mean, I use polynomial because I want to use the sum of squares framework, and the sum of squares framework, at least as it's been developed by pure mathematicians, is primarily for polynomials. However, you can find all kinds of papers where people apply this to rational systems or to trigonometric systems. Actually, we do a trigonometric example in our paper together. So, but the whole point is, if you use functions that are not polynomials, you have to come up with clever tricks to change everything into polynomials, okay? So in my case, just by using the library of polynomials, I don't know where to look. In my case of using the library of polynomials, it's skipping that intermediary step of transforming the system into polynomials. So, but you could use anything. And then the other side of this is the computational side, Victoria. If you use something that's not polynomials, you need a parser that's going to transform everything to be solved by an interior point solver to get these SOS programs working. So you're more than welcome to, but it might be more of a headache.
Are there any questions here from the trainees, maybe? Yes.
I have a question. Yeah, you mentioned with the fluid flow regarding the transition to turbulence, it was sort of like a bifurcation. Does this approach work with a variety of different bifurcations that might not be a transition to turbulence, maybe like a transition to oscillations or a
Actually,
fold or a...
this transition is just a saddle node bifurcation of periodic orbits. That's all it is. And then those periodic orbits period double into chaos eventually. But this is just a saddle node bifurcation that comes out of nowhere, right? So you're looking over here and a saddle node happens over here. And that's kind of the takeaway, is that you're just looking for like qualitative differences in the dynamics and when they should be taking place, even though you don't observe them taking place. Because you don't see the turbulence until way down here, right?
Right.
But you want to know what starts, when it
So if
starts.
it was something like a Hopf bifurcation to oscillations, would this method also be
Yeah.
work in the same way?
But if it's a hot bifurcation, these curves are going to be nice and smooth, right? Because maybe you have your time average at a steady state. Steady state destabilizes and a little tiny periodic orbit comes off of it, right? So you're just going to see it's going to be a nice gradual lift off.
I see.
So, but the reason that would be potentially less interesting is because I already knew the state was there, right? What's most interesting, you find this in systems of coupled oscillators with the onset of synchrony as well. You just have these sporadic saddle nodes and everything changes without you noticing in some regard. And that's what you want to try and detect here.
No questions? So I had a couple actually, quickly. So what is hidden in, this is naive questions, of course, what is hidden in the word ergodic? Like what constraints are hidden in that?
So, okay, ergodic has a very precise meaning going back to the days of Koopman. So it's von Neumann and a bunch of Birkhoff, a bunch of Koopman's colleagues at Harvard. And what it really means is that, okay, so if you let the system.
So I get the time average equals sample average.
Okay,
That's what I got. The question was different. Like so when is the time average not the sample average? So when does your method break down? Under what conditions? When is it non-ergodic as a practical example?
Well, okay, it will be, if your system is non-chaotic. So for example, my Van der Pol oscillator, right? That thing is only ergodic on a measure that's supported on the periodic orbit and the unstable state. So in that case, what comes down to the definition of, like, every system can be proven to have an ergodic measure. Problem is whether or not it says anything useful about the system.
Yeah.
So when it comes to a chaotic system, you have this sort of full-bodied chaotic attractor that has all kinds of information in it. And the measure is over the whole thing, right? So it's over something that's not nothing in some regard.
Yeah.
Whereas if you think about this van der Pol example, the measure is completely supported over like things that have no no measure in phase,
But-
no Lebesgue measure in
But
space.
shouldn't the starting point
Sorry.
dependence imply that the sample averages can be very different from the time averages?
No, that's what's nice about the time average, right? The time average gets rid of all of the transients. That's why we use it for chaotic systems. So same thing here, the time average will eventually converge onto the periodic orbits time average because it gets rid of that. That's why we don't care about pointwise evaluations of the energy. That's why we care about the time
We
average.
can continue this later.
Yeah, sorry. Okay, yeah.
Great. So any other questions? No, then thank you very much.
Thank you.
Stop the recording.